welcome back. And we're officially going to kickstart our discussion on a problem related to calculating pH and pOH for a weak acid and a weak base. All right. So I'll have an equation here. And this is kind of what you did in lab. And this is vinegar, which is nothing but acetic acid. So it's not one of the acids on the 6 strong acid list. So we can safely assume it's a weak acid. So this is a base. So this is the conjugate base, and this is the conjugate acid. And the fact we know we've made an H3O plus indicates we got to use Ka expression. And before that, let's actually write the problem. I'm asking you to find the pH of a 0.25 molar acetic acid at 25 degrees Celsius. The temperature is key here because the Ka value that is reported in the problem is for 25 degrees Celsius. Even though you don't actually use the temperature in the calculations, it is given in the question, just so you know. It's not a distractor or meant or purposefully given to throw you off or anything. It's just the way the problem is written. This is the temperature at which this value is measured. I have to provide you with this value, otherwise you cannot solve this problem. Right? So I'm going to rewrite the equation I showed above. Now, as I said, you have H3O plus, so you're going to write Ka expression, which is your product concentration over your reactant concentration. You don't include water in the expression, right? Let's understand what we are trying to do before we actually solve the math. If we can find this, okay, which is one of the product, if we can find this, then we can find pH, because that's what you are familiar with, right? But if you've seen the video on concentration of pH of strong acids and strong bases, this is quite different. While I really don't want to use the term ice, you know, when you're in Rome, be a Roman. You're teaching a chemistry class, get along with the chemistry community and say a couple of things every now and then that they all do. And that is ice table. Okay? Now, all of this just makes the problem looks like it's a big deal. It's complex. Imagine a chihuahua that keeps barking 24/7, 365 at even a shadow, a moving grass, thinking it's a big dog. Okay, it is not. It's nothing but an annoying creature, right? Whereas a Rottweiler barely says a word, or a Great Dane, or one of the big dogs, or a Newfoundland or Great Pyrenees. These dogs don't shout. Okay, they just keep calm, but they know they're big, right? A Chihuahua is like a little dog, and it just keeps barking, right? This problem is like that. It looks like it's big and huge, and looks like it's complex, but it's really not. Okay, the reason I say that a couple of times is because it's just what it is, right? Okay. And the format of this ice thing is very much the same. There is a couple of exceptions, but we're gonna just stick with what is conventionally asked on standardized exams outside of a chemistry class. So the I stands for what is your initial concentration? What are you starting with? Well, you're starting with 0.25 molar. Typically, I leave H2O blank, and the concentration of these two are 0. Well, think about this. If you just begin a weight loss or some kind of fitness training, you don't expect to see that result the same day, right? You can look in the mirror for 24 hours after you worked out. You're not going to see a change right away. Same thing, when you just begin a chemical reaction, you're not going to see a product right away. Okay, even for strong acid, strong base. It takes a few seconds. So we're going to say at the start, there are no products, so it's 0. And if you want to know why I put a blank for water, that's a discussion for some other time. And C indicates what is going to be the change that we're really interested in measuring. Because reactants are typically lost during the course of the reaction, they get a negative X. Now, I will do one problem later down the road where things will be slightly different. Again, we're going to keep this blank. Because we're losing reactant, but we're making products, we give plus x. Now it's plus x because it's all 1, 1, 1, 1, 1, 1. If this were to be 2, then you put 2x here. But it's 1, so 1x. Equilibrium would be just basically add those two. It's 0.25 minus x, blank, 0 plus x is x, 0 plus x is x. This is key. This is what we're really interested in. Now we're going to put all of these in place of these species on this equation. So what does that mean? So Ka equals, well, this right here is x, so it's x. This right here is x, so it's x. This right here is 0.25 minus x, right? Now this equals to the Ka value, which is basically 1.8 e to the negative 5. From this point on, it's math. It's no longer chemistry, okay? Now I do want to point out something is, if this Ka value is negative 5, negative 5, negative 6, negative 7. As it becomes more and more negative, we can make the assumption that 1.8 e to the negative 5 equals x squared, because x times x is x squared. We can make the assumption that this 0.25 is much, much bigger than this x, so we can avoid a quadratic equation. Okay, this is a key. We've made an assumption to simplify this equation even further. We didn't simplify the numerator, but we did simplify the denominator. So we can now find x. X squared equals basically 1.8 e to the negative 5 times 0.25. So that would be, let me get my calculator, 1.8. 1.8 e to the negative 5 times 0.25. Okay, so that's, and then this right here equals 4.5 e to the negative 6. So x equals square root of 4.5 e to the negative 6, which would be 0.0021. Okay. What is this x really? X is H3O plus. It is also CH3CO minus, but it is also H3O plus, right? What do we need to find pH? We need H3O plus, exactly. So negative log of H3O plus equals negative log of 0.0021. So pH equals just log of that. Negative log of that would be 2.67. So if you know pH, what's pOH? Well, that's 14 minus of that value, right? 14 minus 2.67, right? That's 11.33. Even though I didn't ask you to find it, you can find it because now we know pH. So I'm going to get out of the full screen mode so you can use some colors to point out exactly what areas issues may arise. First area is you're putting them in the right order, okay? These go in the numerator. This goes in the denominator. It's the first area to remember. The second is this assumption, okay? Which is, oh, let me actually circle that. Circle this. If your Ka value is negative 5, negative 6, negative 7, negative 7, then we can assume that this is big and just get rid of it and write it without the minus x. What this does is this avoids a quadratic equation, okay? And then from here, this whole area is important because No matter how much time I can spend, ultimately you just have to know that how to put these things in a calculator. Okay, like squared is basically you cross multiply these two, you know, and then you get this and take the square root. So this right here itself is the H3O plus value. And then from there you find pH and pOH. So whatever I've circled or drawn in blue, those are the areas you may have to pay attention after you finish watching this video. You can watch it every time from the start, but I want you to pay attention to these areas drawn in blue so that you know that's kind of what is expected out of you. All right. So I'm going to stop here. This is how you calculate pH and pOH for a weak acid. I'm going to do one more problem for a weak base so you have both weak acid and weak base. All right. So stay tuned.